In this video, we're going to discuss nuclear chemistry. And to start this, we need to go back to talk about our isotopes. So if you think back far enough in chemistry, you might remember your hydrogen 1, your hydrogen 2, your hydrogen 3, maybe your carbon 12 or your carbon 13. That upper left tells us the number of particles in our nucleus. We're also going to introduce what's on the lower left. Lower left is going to tell us the number of protons. So there's 1 proton in hydrogen. There's 6 protons in our carbons. This helps give us a quicker reference for how many protons and how many neutrons we have. Top minus the bottom tells us our number of neutrons. So if I'm looking at my protons and my neutrons, I'll get 1 proton and 0 neutrons. I have 1 proton and 1 neutron. 2 minus 1 equals 1. Over here, I have 1 proton because it's hydrogen, and I have 2 neutrons. 3 minus 1 equals 2. For my carbon, 6 protons and 6 neutrons, or 6 protons and 7 neutrons. If you have the same element, but a differing number of neutrons in its nucleus, you have different isotopes. Some isotopes are stable, and some are radioactive and can decay. So we're going to explore what does it mean to decay, how do we do it, what are the different forms, and what are the different types of radiation, and how we interpret those different radiations. Our first form of decay is our alpha decay. An alpha particle is really a helium-4 nucleus with a 2+ charge. It is 2 protons and 2 neutrons. What will happen is if you have a large nucleus with many protons and many neutrons, it's possible it can decay by ejecting 2 protons and 2 neutrons. In this process, you'll have something like uranium-235, and it will convert. It'll make 1 alpha particle. And well, what happens to our uranium? It loses 4 things from its nucleus. So it's no longer 235, it's 231. 2 of them were protons, so it only has 90 protons now. It's no longer uranium, it is thorium. In a normal chemical reaction, we cannot change what the element is, but in a nuclear reaction, we do. Our uranium, when it breaks off that alpha particle, ends up leaving behind only enough protons to be considered a thorium. Well, when this breaks off, it doesn't go quietly. It streaks away at incredibly high speeds and can impact and break bonds of other things, steal electrons. We'll talk about the damage it can do, but this is one form of radiation. An alpha particle is a helium nuclei busting out of a larger nuclei. Well, there's alpha particles, and there's beta radiation. Beta radiation is an electron. These may be written as beta 0 with a -1. There's nothing in its nucleus, and it has a -1 charge because it's an electron. But you may see it in this form when we're talking about radiation. Well, what happens here is it's not an electron that's on the atom. This is an electron that's formed in the nucleus. Rather is I'll have a neutron, and that neutron is going to break into a proton and an electron. So in our atom, we'll have some neutron here that suddenly just becomes something else. It becomes a proton instead. When an electron gets formed, and electrons don't take sizes as small as the nucleus, it has a much bigger wave function, it can't exist there, it gets ejected. Well, this is significantly lighter in weight than an alpha particle. It takes an enormous amount of energy with a very light particle. This travels at a very good fraction of the speed of light. This is a very high energy electron. Processes that can cause this are things like carbon-14. Carbon-14 can break into nitrogen-14 and an electron. Think about the processes that happened here. I had protons and neutrons, 6 and 8. Afterwards, I have 7 and 7. I have 1 more proton, I have 1 less neutron. How did we do that? A neutron decayed into a proton and an electron. Part of why we have to make both, you can't create or destroy charge in the universe. When one gets made, the other also has to be made. If one gets removed, the other also has to get removed. Total charge must be balanced. And so part of the decay process for our neutron is that it creates one proton and one electron. Generally, while bound within nuclei, neutrons are stable, but an imbalance in the number of neutrons and protons beyond a certain range can leave some of the neutrons prone to decaying. A free neutron, however, decays rather rapidly, has a very short half-life. Well, we have our alpha and our beta, and we can also have gamma. Gamma radiation, also sometimes symbolized as gamma 00, these are just photons, very high energy photons. Think back to light. You had your visible spectrum, you had your ultraviolet, you would get up into your X-rays, and then into your gamma rays. Gamma rays are some of the highest energy photons, and in fact, some of them are so high energy we can't figure out physical processes that can make them. We detect a few from space every once in a while that are just well beyond what should be possible. We figure they come from black hole collisions and the like, but we're not exactly certain yet. Within nuclear chemistry, these are kind of the highest obtainable normal sources. This just happens when the nuclear decay has a residual energy that it can't impart to an alpha particle or a beta particle. In fact, a lot of gamma radiation accompanies alpha and beta decays. They're also emitted at the same time. Though in some cases it is possible to just have a gamma decay. You can have an excited iron situation where it decays into a lower energy iron nucleus and some gamma radiation. This particular situation comes from other reactions where we have a cobalt that decays into iron, but that iron is in an excited state for its nucleus. The arrangement of the protons and neutrons coming from its change from cobalt are higher energy than it could be, and so it relaxes, giving off that energy as a gamma particle. And so a lot of times this is accompanied in a decay series or just along with another type of decay. This is very useful for Mossbauer spectroscopy, where we can actually see the binding environment of iron and how energetic it is, how much the electron density around the iron is, and its oxidation state. In addition, it's actually more related to our beta from earlier, there's a beta plus, positron. In this case, we can have something like carbon 11 break down into boron 11 and a beta particle, beta plus, and a positron. What's happening here? My protons, my neutrons, 6 and 5, and then 5 and 6. I've lost one proton, I've gained one neutron. So effectively, a proton has converted to a neutron. But we can't get rid of that positive charge. It is necessary that the charge remain constant in the universe, and so this creates a positron, which for all intents and purposes is just the antimatter electron. All the properties are the same except it is positive instead of negative. So we can actually observe antimatter creation by watching the carbon-11 decay, and we do this regularly. PET scans, positron emission tomography, actually will give a patient sucrose laced with some carbon-11. They'll ingest it, it spreads throughout the body. Well, it starts to break down. Cells that are using more energy need the sugar sooner, and so brain material, which is heavily driven by sugar, and cancer cells tend to acquire this sugar the quickest and concentrate it. And so if you have a person, and what you see as you monitor them is a couple random spots of radiation explosion, and then a lot here, and a lot right here. We expect a little bit from everywhere, but if there's a concentration of it, it's because something there is concentrating that sugar. This symbolizes that right here, we probably have some kind of tumor. How does it accomplish this? How do we see the emissions? Well, the positron doesn't make it very far before it runs into a regular electron. And if you get a beta and an electron interacting, they just go to a lot of gamma. It's an antimatter explosion, and it happens in your brain. It gives off some energy, it does some damage locally, but these are on a fraction of a fraction of a fraction of a mole. Your body can take some damage. As we'll get to radiation and its effects, we'll see that a little bit of radiation doesn't do much, but our systems are sensitive enough to pick up individual decay events. And so we can see only a couple decay events in order to spot where they're coming more commonly from. Doesn't do enough damage to really hurt the body, and so we can use it to locate tumors. Despite that, it's just fun to point out, yes, we cause antimatter explosions inside people's brains. Within nuclear changes as well, there's also electron capture. So instead of a nucleus breaking down and emitting something, what will happen is a nucleus will capture this electron. In this case, you'll have an electron plus a proton becomes a neutron. This actually happens in our formation of carbon-14. Nitrogen-14 becomes carbon-14 in this process. High-energy beta particles from space bombard the Earth's atmosphere. We have a lot of nitrogen. Randomly, what will happen is some nucleus will have an electron that gets hit hard enough that they get captured. This becomes neutral. And the net result is if we look at our protons and our neutrons, it was 7 and 7, and now it's 6 and 8. One of our protons went away, we gained one neutron. This is how the carbon-14 on Earth actually forms, and this is why it's good for carbon dating. The universe tends to attack Earth with a fairly consistent amount of high-energy beta particles. We've had a pretty consistent amount of nitrogen in our atmosphere, so the production of carbon-14 is pretty constant. Well, it's radioactive and eventually breaks down, so we'll build up a certain level over time of carbon-14 until the rate of decay matches the rate of production. There's an equilibrium amount of carbon-14 floating around the Earth because of this. However, if you have a small little plant and carbon-14 gets into it and the plant keeps growing, well, that carbon-14 is not mixing with the Earth. It's not getting the constant replacement matched to its decay. And so whatever amount of carbon-14 it's had in there, when the plant dies and gets buried, that carbon-14 starts to disappear over time and is not replaced. And so later when we come along and look at how much carbon-14 is in some ancient fossilized piece of wood, we can use that to figure out how long ago that tree stopped pulling carbon in from the atmosphere. So an example where electron capture plays into things we may have heard of. Carbon-14 dating is dependent on electron capture, making that carbon-14 in the first place. So here's an introduction to the types of decay events that can occur in a nucleus, how it plays out in changing the different atoms between different types of elements, as well as the isotopes. We'll use these terms as we continue, but here's a quick refresher and an introduction to the ideas of radiation.